So in this video, we're going to look at factoring, all the way from the basics for factoring out common denominators, also common factored problems like sum and difference of cubes, difference of squares, perfect square trinomials, and we're also going to look at the reverse foiling. So we're going to look at all the different factoring techniques, factoring by grouping, lots of different things in here. If you're doing this as a review, then this will be a pretty comprehensive review. If you're learning this for the first time, of course, take it slow because there's a lot going on in this video, and we'll go through lots of worked examples. So typically, anytime you have an equation that's larger, has a higher degree than a linear equation, you're going to need factoring at some point. We needed to simplify rational equations, radical problems. You're going to use it a lot in differential equations if you're going there, definitely in calculus. So this is from algebra on. This is one of the reasons we learn this, is because it's so useful. Now, in general, you should always put your polynomials in either ascending or descending order so that factoring is easier to do. That way, similar things are grouped as close together as possible. That's very important for any term, any expression that has more than two terms in it. All right, so the first thing to do for factoring is generally we need to see if there's any common factors that we can factor out. And so finding the greatest common factor is the first step. Now, that's not the only step, but it is the first step. So let's look at an example of finding the greatest common factor for this example, x to the fourth y minus x y to the fourth. Now, what we're going to have to try to do in this case is we're going to have to find the largest power of x or y that is common to both terms. And in this example, both terms have an x and both terms have a y, but in the first term, it's only y by itself with no other powers. And in the second term, it's only x by itself with no other powers. X can always be divided out of x with powers, and y can always be divided out of y with powers. So our common factor here is going to be x times y. And so one way of thinking about how we're factoring is that essentially, as we remove the factor, we're dividing what remains by that factor. So we can think of this as taking our original problem and dividing it by that common factor. And then we separate them out into two expressions and cancel. In this case, we would cancel the y's and one of the x's. That would leave us with just x cubed. And in the second term, we would cancel out the x's and one of the y's, and that would leave us with y cubed. And so, in factored form, this would be our common factor times the expression that remains. Now, this isn't done, but we'll need difference of cubes in order to continue, and so we'll continue this problem in a later example. Let's look at one more example of greatest common factors, and that is with this polynomial 3x squared plus 9x minus 54. Now, every one of these terms has a common factor of 3. So there's a 3 that I can divide out in this first term. 9 divides by 3, and so does 54 divide by 3. So again, what I can think of this as is dividing each of my terms by what I think is the common factor. And then that reduced form would then be the second factor after I take out my 3. So this expression, 3x squared plus 9x minus 54, is equal to 3 times x squared plus 3x minus 18. And if I want to verify that, I can distribute that 3, and I should get back my original expression. Now, this is not also finished factoring. This is just the first step. And so we'll finish this example in another example later on. Always, always, always look for the greatest common factors first. That's going to make all the other steps that you have to do much easier. And even if you find one common factor, it's always a good idea to check the expression that remains and see if you've missed any. because it can be a process of repeated simplifications. All right, now once we have the greatest common factor separated, then our next step is to look for any special formulas. Because the special formulas have particular ways of doing the factoring, and they're not going to necessarily always yield to some of the other techniques that we'll be looking at later. So we're going to look for those special formulas. And so basically we have three things that we want to be looking for. If we have cubes to an expression, a binomial expression, both of which involve cubes, then there's a formula for the sum of cubes and for the difference of cubes. If you have a cubed plus b cubed, then the first factor is a plus b, and the second factor is a squared minus ab plus b squared. Notice that in this first factor and in the second factor, those signs are opposite. The b squared is always positive. In the difference of cubes, we have a cubed minus b cubed, and the first factor would then be a minus b, which matches the original sign in the binomial expression. And then in the second factor, a squared plus ab plus b squared. And again, notice that the middle term and the smaller factor, they have opposite signs. The difference of squares formula comes up a lot. If you have a squared minus b squared, then this is going to factor as a plus b times a minus b. And then the perfect square trinomial is going to have the form a squared plus 2ab plus b squared. And this is going to factor as a plus b quantity squared. And if you have basically the same thing, but with a minus sign, then that will factor as a minus b quantity squared. Now, we'll see some examples of figuring out exactly whether our formula exactly fits this perfect square trinomial. But once you identify it, then the factoring is straightforward. Now, let's look at a difference of squares example. This is the continuation from our first example. We had factored out the xy, and now we had one factor that was x cubed minus y cubed. Now, we want to factor that, and since x cubed and y cubed are both perfect cubes, we can apply the difference of cubes formula, where x is equivalent to a in our formula and y is equivalent to b. And so that factored form is x minus y, and the second factor is x squared plus xy plus y squared. And again, if you want to check it, you can always FOIL it out and make sure that like all the squares and linear terms do in fact cancel. That's why these factors are chosen this way. So what we have, once we've factored this expression, we have a complete factorization of our original x to the fourth y minus xy to the fourth. We have our greatest common factor xy, and then the remaining cube factors is x minus y and x squared plus xy plus y squared. Now, the sum of cubes is going to work the same way, but here we have coefficients and not just variables. For problems like these, it's always a good idea to kind of keep in mind what your common cubes are. Usually you don't have to learn all that many of them. 5 or 6 of them is usually enough, but it is worth memorizing the sort of smallest ones that show up most frequently in textbook problems. Now, in this case, always start with the greatest common factor to see if there are any. In this case, the cubes kind of suggest this is a perfect cube problem, but 16 and 54 are not perfect cubes. So in this case, I'm going to look for greatest common factor. They're both even. 54 does not, however, divide by anything bigger than 2. So I'm going to factor out a 2, and that's going to leave me with 8q cubed plus 27p cubed. And 8 and 27 are in my list of perfect cubes. 8 is 2 cubed, and 27 is 3 cubed. So I want to think about my initial expression here as being 8q cubed is equal to 2q quantity cubed, and 27p cubed is equal to 3p quantity cubed. And so that's how I'm going to put these into my sum of cubes formula, where I'm going to let 2q be equal to A, and I'm going to let 3p be equal to B. And so that's going to give me, the first factor will be 2q plus 3p. And then in the second factor, that's A squared, so that's 2q quantity squared, which when I multiply that out is 4q squared. And then AB minus AB in my middle term will be 2q times 3p, which will give me 6pq. And then the last term is B squared. And so that's 3p quantity squared. And so if I multiply that out, I get 9p squared. So this is my final factorization. I have the 2 that was the greatest common factor, and then my 2q plus 3p. And my third factor is 4q squared minus 6pq plus 9p squared. Now, in this sum and difference of cubes formula, this quadratic term is not further factorable. So you don't have to go any further than that. Now let's look at difference of squares formula. So in this case, we have x to the fourth minus 1. All even powers of x are squares of something. And we then also have to have our constant be a perfect square, or our other variable be a perfect square. And again, it's useful to think about what your common perfect squares are. You probably should know more squares than you do need to know for cubes, probably like twice as many. But there are, up to 15 or 16. Those show up relatively frequently. And then things like 20 or 25 also do occasionally show up. So 1 is obviously 1 squared. So for this particular example, we don't need all of these. But in a general case, you might. Now, in this case, we're going to factor this into fact 2 times. X to the fourth is equal to x squared quantity squared. So in our difference of squares formula, A is actually going to be equal to x squared, and B is going to be equal to 1. And so we can factor this as x squared plus 1 and x squared minus 1. Now, x squared minus 1 is itself a difference of squares. And so that would then have to be further factored into here. A would just be x, and B would again be 1. And so this would be further factored into x minus 1, x plus 1. It's very tempting to stop after the first set of factors. But you always have to look at what you get as a result of factoring and see if it can be factored further. Now, the sum of squares cannot be further factored. And so we have to replace x squared minus 1, but the x squared plus 1 can't be reduced. And so our final factorization for x to the fourth minus 1, is x squared plus 1 and x minus 1 and x plus 1. So we end up with 3 factors. And then the last example that we wanted to look at was that perfect square by trinomial. And so this is an example. Again, we want to start looking for, are there any greatest common factors? That's always our first step. In this case, 16 and 72 have common factors, but 16 and 81 don't have any common factors. And so once we've gone through the coefficients and said, yeah, there's not any that divide into all 3 of them, then we can assume there's no greatest common factors. So what we're going to look at is, if this is a perfect cube trinomial, then the first term and the last term have to be perfect squares. And the 16 is in fact a perfect square, and m squared is a perfect square. And so that is equal to 4m quantity squared. And then the last term, our other perfect square, is 81n squared. 81 is the square of 9, and of course n squared is the square of n. So this whole expression is 9n quantity squared. So for inserting into our formula, A is 4m and B is 9n. But the fact that the ones on the end are correct and they're perfect squares and they match doesn't guarantee that this is a perfect square trinomial. Instead, we have to also check that middle term. And for that middle term, it needs to be equal to 2ab. So we're going to take the a that we determined from our first term in the trinomial, and we're going to take the b that we determined from the third term in the trinomial, and we're going to multiply them by 2 and each other. So 2ab becomes 2 times 4m times 9n. 2 times 4 is 8. 8 times 9 is 72, and then mn. And that does agree with our middle term. And the middle term is negative, and so the formula we're going to use is also going to have a negative. So this will be a minus b quantity squared. So 4m minus 9n quantity squared. And then if you, of course, FOIL, you'll see that you do, in fact, get back to the original expression. Now, one other type of factoring that we need to deal with is factoring by grouping. And factoring by grouping is something that you tend to do on term expressions that have 4 terms. They might have different variables in them. They might all be the same variable, but differing degrees. Cubes that have 4 terms can be often factored this way. But they can actually be, this grouping process can actually be applied anytime you have an even number of terms. You can always try it. So 4 terms, 6 terms, 8 terms. And in this case, we're going to try to, you may have to rearrange the terms sometimes, but you're going to try to put these together in groups of 2 where you can find some common factors among the pairs of terms. So here, this is already ordered in a way that allows us to do that. So if I take the pq plus 5q, which is the first 2 terms, both of them have a q. And so I can factor the q out and rewrite those 2 terms as q times p plus 5. And in the second 2 terms, 2p plus 10, there is only a 2 in common. So I can factor that out from those 2 terms, and the parentheses that I have left is p plus 5. Now, so that's going to give us our first level of factoring. But we're not quite done, because what we see is after we've done this, we have a common term in the p plus 5 in both of these 2 pieces. And so we're going to factor out the p plus 5, and we're going to leave behind in our second factor what had been our greatest common factors in those 2 pieces, the q and the 2. So, and take the sign in front, in between the 2 terms. So p plus 5 is what they have in common, and q plus 2 are those 2 factors that the p plus 5 was multiplying. If this seems kind of complicated, you can always also do this thinking about it like a substitution. So if you replace the p plus 5 with a dummy variable like u, then that reduces the expression that has so much stuff going on into q times u, your dummy variable, plus 2 times u, which is a dummy variable. And then it may be easier for you to see that, oh yeah, there is a u in common. And when you apply your greatest common factor, you end up with u times q plus 2. And then you can put the p plus 5 back into the expression, and you'll get the same result that we had before. And you may want to do this to get started until you feel more comfortable with it. And then you'll kind of recognize that this is just sort of a longer way to get to this. And when you feel more comfortable with it, you'll be able to go directly to this instead of going through the multiple steps. And of course, if you're not sure, it's always a good idea, especially when you're learning this, or if you haven't done it in a while, to FOIL everything back out and make sure that you got back the original expression. Now, the second example we have for the factoring by grouping is going to involve a cubic expression. And this is kind of the other situation in which the factoring by grouping will tend to come up. But it basically works the same way here. We're going to collect our first 2 terms together, and x cubed and x squared have a common factor of x squared. And so we're going to factor the x squared out and leave behind 1x and a 3. And then in the next two terms, the negative 5x and the negative 15, we're going to factor out what they have in common. Now, it might be tempting to factor out just the 5, but in fact, you need to factor out the negative 5 in this case. And when you do that, you're going to leave behind an x and a positive 3. And remember, that's what we need, is we need an expression for factoring by grouping to work where we have a factor in both of these expressions now that have something in common. And they have to be identical. They can't be kind of the same. They have to be exactly the same. And so when we have x plus 3 and x plus 3, that becomes our new common factor. And what's left behind is what was in front of these parentheses, in this case, x squared minus 5. Now, 5 is not a perfect square, so we can't actually factor this any further if we're using just whole numbers. But if this had been a 4, we would have been able to factor one more time. But 5 is not a perfect square, so we can leave it like that. Now, the very final step after finishing all your greatest common factors and your special products, the sum and difference of squares, or the sum of difference of cubes, the difference of squares, or your perfect square trinomial, is to then do any of the remaining factoring that still needs to be done. If you have a quadratic, there may be ways to factor those into binomial expressions, and that's the last thing that we have to look at. So if we have a quadratic like this, an x squared expression, we want to look at the factors of the last term when it's this simple that might add to the middle term. So what are the factors of 12 that are available? Well, we've got 1 and 12. That doesn't add to 8. 2 and 6, those do add to 8. 3 and 4 adds to 7. So the one that we want is we want the factors for 2 and 6. 12 is positive, so both of these factors have to have the same sign. And because the 8 is positive, we want them to add to positive 8. And so they're both, in fact, positive. And again, you can FOIL this back out to see that this will, in fact, when you FOIL it out, give you exactly this expression. So again, what you're doing here is if there's no leading term in front of the x squared, you're factoring the constant, and then you're trying to see if this is a positive, which factors add to the middle term. And if the middle term is negative, then it will basically still work the same way as we see in the next example, only that you'll need them to add to a negative number, in which case both of your factors will be negative, because negative 2 times negative 6 is still positive 12. Now, in the case where the last term is negative, then you're looking for factors of this last number which have a difference of the middle term. So in this case, factors of 18 are 1 and 18, 2 and 9, and 3 and 6. It's 3 and 6 that have a difference of 3. And when you are writing out these factors, again, you'll put in the 3 and the 6. The larger one will have the same sign as the middle term. And so this will be a plus 6 and a minus 3. And again, you can check this by FOILing, because you're going to get a plus 6 and a minus 3, which is going to partially cancel and leave you with a plus 3. If the middle term was negative, then you would make the larger factor negative, and that would be equivalent. We did number 2, example 2 previously, where we were just factoring out the common factor. In this case, we ended up with exactly this expression, x squared plus 3x minus 18. And so we can finish factoring example 2, take out the common denominator, and then factor the quadratic that is left as x minus 3 and x plus 6. Now, when the leading coefficient isn't 1, this can be a little bit more complicated. And there's 2 types of ways that you can go about doing this. There is a technique called factoring by grouping, and the other is trial and error. We're going to do some examples by trial and error, and then we'll also do one example with grouping. Now, when the factors for the first and leading terms, first term and the last term, are few, then there aren't a lot of trial and error things that you have to test. So 2 factors has only 2 and 1 as factors, and there's no other options. And 3, likewise, only factors as 3 and 1, and so there aren't any other options. And so our only concern here is to try to figure out, does the 2 multiply the 3 or does the 2 multiply the 1? And so these are our only sort of forms of factors that we can have for this particular expression. And our solution, since all of these terms are positive, all of these parentheses will also only possibly be positive. And what we would have to do is we would have to just put in the parentheses, put in the addition signs, and then FOIL them out to see which one will actually get us that 7 that we need for the middle term. Now this is, if there's a lot of factors, then this can be a lot more to check. With practice, you can get really good at sort of identifying what's likely to be the most likely to be the correct result versus which are the least likely to produce the correct result. Generally, I prefer to start in the middle term, the factors that are the closest together, and kind of work my way out. Textbooks often don't have really, really giant middle terms relative to the outside terms, so that tends to limit the differences between the factors that you have to consider. But what we want to match that 7m in this expression. And so what we're going to do is we're going to do the OI terms of our FOIL, so the outer and the inner terms, and add them up to see which ones match. So 2m times 3 is going to give us 6m, and then 1 times m is going to give us m, which does add to 7m. If we do it the other way, we'll get 2m times 1, which is 2m, and 3 times m, which is 3m, which only gives us 5m. So that one isn't going to work. The one that does work is this first way of factoring. And so our final factor is 2m plus 1 and m plus 3. And again, if you can verify by foiling that this does in fact produce this result. Now, as I said, trial by grouping or trial and error can become very complicated when you have a number like 24 and 30, which have multiple ways of factoring. So 24 can be factored as 1 and 24, and 2 and 12, and 3 and 8, and 4 and 6. And 30 can be factored as 1 and 30, and 2 and 15, and 3 and 10, and 5 and 6. That's a lot of options. But again, my strategy typically, and this works for textbook problems, is to start with the pairs of factors that are most similar. So in this case, 4 and 6 for the 24, and 5 and 6 for the 30, and then look at those problems. Now, in this case, the 30 is negative. So what that tells us is that our factors are going to have different signs. One will have to be positive, one will have to be negative. And so in addition to matching the 71, we will also have to match the sign. Is it positive 71 or negative 71? All right, so let's look at, just looking at the 4 and 6 and 5 and 6 combinations, the possible combinations of those factors that we can have, given the change in sign, is the 4 coming first and the 6 in the second factor, and then pairing that with 5 and 6, or 6 and 5. And in this case, the first factor is positive and the second factor is, the first factor is negative, second factor is positive, or all those 5 and 6 and 4s all in the same order, but with the signs flipped. Now, as it turns out, there are reasons that we might want to eliminate some of these factors to start with. So for one thing, if 6x plus 6 or 6x minus 6 was in our original problem, then there would be a common factor. There's a common factor in this factor, and therefore there would be a common factor in our original problem. And there is no common 6 in the original problem that would have reduced the work that we were doing. So we can eliminate both of these options. And we can actually say the same thing for the second choice of options. 4 and 6 have a common factor of 2, but our resulting polynomial doesn't have a common factor of 2. And that would have to be true if this was an appropriate factor combination. So since none of these are going to work, then what we want to do is we want to try a different combination. Either change out the 4 and 6 to 3 and 8, or change out the 6 and 5 to 3 and 10. Don't change both, because you need to check all of the different combinations. So change one of them. So I'm going to try changing out the 4 and 6 to 3 and 8. And again, all the sign combinations that we saw before, they're still operative. So the 3 can go, and the 8 can go with the 5, and the 8 with the 6, with a negative sign and positive sign, or the reverse. Or we can put the 3 with the 6 and the 8 with the 5. Now, these can also be eliminated for the same reasons we saw before. 8 and 6 have a common factor. Our original problem doesn't have a common factor, so both of these are out. Same for 3 and 6. 3 and 6 have a common factor of 3. The original problem doesn't have that, so they can go. So let's try 3 and 8 with 3 and 10 instead of 5 and 6. So here, again, we're taking the previous combinations and we're replacing the 5 and the 6 with the 3 and the 10. We can eliminate these top ones because 8 and 10 have a common factor and 3 and 3 have common factors. That would give us a common factor of 6 in the original problem. That doesn't exist. So let's try this one. These don't have any common factors, so let's FOIL the middle terms and see what we get. So 3x times 8x is going to be, 3x times 3 is 9x, and then negative 10 times 8 is 80, and 9 minus 80 is negative 71. And this is going to be the same thing, but with the signs flipped. So 3x times minus 3 is minus 9, and 10 times 8 is positive 80, which gives us positive 71. Our original problem, if we go back to the beginning here, was a negative 71 in the middle. So this is the one that we want. This is the correct factorization. Now, if this had not worked, of course, we would keep going. We would try maybe combining the 3 and the 10 with the 4 and the 6 from the 24. And we would just keep going until we had tried all the possible combinations or we found a factorization that had worked. Now, there is another way to do this when these factors, these combinations of factors get very complicated. And we're going to look at that. It's called factoring by grouping. Now, the main drawback with factoring by grouping is that in order to figure out how to separate these 3 terms into a combination of 4 terms, basically by splitting up this middle guy, is that you're going to have to multiply the coefficient on the front by the constant on the end. And sometimes this is called the AC method because in a quadratic expression, this is the A coefficient and this is C, and you're multiplying them. Now, the problem with this is that you can get very large numbers and then you have to worry about, well, how do I factor? How do I find all the possible factor combinations of this really large number? But we're going to go through that to start with. So 24 times 30 for this factoring by grouping method is equal to 720. And so we're going to need to find factor combinations of 720. Now, there is a way to do this with the calculator. And basically, you're going to take, it's like if you have a TI, you're going to put in your y equals screen, the number that you're trying to factor divided by x, and then go to your table starting at 0 or 1, and then your step size is 1 and put it on auto. And in the table, then it's going to give you, it's going to divide the 720 by X. 720 by 1, 720 by 2, 720 by 3, 720 by 4. And these are then going to be factors of 720 that multiply to 720. So 1 and 720, 1 times 720 is 720. 2 times 360 is also 720. 3 times 240 is also 720. 4 times 180 is also 720. 5 times 144 is also 720. 6 times 120 is also 720. And if you keep going until you get to the point where the factors start repeating themselves. So we also have 8 times 9 is 720, 9 times 80 is 720, 10 times 72 is 720, 12 times 60 is 720. If you're getting decimals, they're not common factors. 15 times 48 is 720, 16 times 45, 18 times 40, 20 times 36, and finally 24 times 30, which was what we started with. Now, what we're looking for is a set of factors here where the difference is 71. And it's the difference because that constant on the end, the 30 was in fact negative. So that's still going to be our sign. If it's a positive, we would look for a sum that adds to 71, but since it's minus, we want to look for a difference. And again, it's the last constant, not the middle term. It's that last constant that tells us, do we want the sum or difference? So since negative 30 was negative, we want a difference of 71. So we're going to just look. 720 minus 1 is not 71. 360 minus 2, that is not 71. And if you keep going through all of them, eventually you find 80 minus 9 is equal to 71. So that's the pair we need. So what we're going to do is we're going to rewrite this negative 71 as minus 80 plus 9. Again, the larger one is negative because the final sum, the middle term, is also negative, but the signs will then be opposite. So this will be negative 80 and plus 9. Now we have 4 terms, and now we can use our factoring by grouping in order to simplify this further. So we take our 2 terms, 24x squared minus 80. What do they have in common? Both of these numbers divide by 8 and x. They both have an x. And 24 divides by 8, 80 divides by 8. So we get 8x, and then what's left over is 3x minus 10. And then we take our second 2 factors, and what do they have in common? Well, they only have a 3 in common. And when we take that out, we're left with 3x minus 10. Aha, they match. And so now we can take out the 3x minus 10 as the common factor, and the second factor is 8x plus 3. And this agrees with the result that we got from the trial and error. Now, trial and error is kind of tedious. It can be very time consuming, particularly when there are large numbers of factors, as in this example. But with practice, it does get much easier. On the other hand, the factoring by grouping, you do have to deal with those very large numbers. And so if you have fewer factors, it works pretty straightforwardly. But if you have very large factors, you do have to be very careful to make sure that you are getting all of the possible factor combinations. And so that is sort of the tricky part for that particular thing. And then finally, in step 4, you want to make sure that anything that you have left is in fact either linear or is not factorable. There are some types of expressions that we can't factor any further. We've seen some examples of, like, sum of squares, for instance, can't be factored any further. But there are other cases. These kinds of factors are referred to as prime, on the idea of prime numbers, that they don't have any other common factors. And so when a problem tells you to factor completely, you can't stop until you literally have factored everything. And so you always have to double check to make sure that if you have any quadratics left over, unless it comes from like the sum and difference of cubes formula, which already we know actually doesn't factor any further, or the sum of squares, that in fact you've gotten to a point where you can't actually go any further. So like for an example like this, this is a leading one, and so we just need factors of 16, and we want to see if we can find any that have a sum of 6. Well, there's 1 and 16, that's 17. 2 and 8 gives me 10. 4 and 4 gives me 8. There are no factors of 16 which are going to add to 6. And so we can say that this is not factorable. Now, when we get to the quadratic equation at some point, there may be an answer, but it won't be a nice, pretty whole number. It'll involve square roots and that crazy stuff. And so when we're just dealing with whole numbers, there are going to be cases where we're simply not going to be able to factor any further. And so this is an example of that. So while prime polynomials do occur, one kind of thing to kind of keep in mind when you're doing these problems, if you're doing a whole section on factoring, if you run into prime examples more than like twice, it's probably not actually the case that you have that many primes. When you're being tested for your factoring skills, we're asking to see your factoring. And so if you're getting like 5 answers that you think are prime, that's a red flag that you're missing a bunch of things that actually can be factored further.